Good evening. Um, I have to thank two people before I start. One is Mr. Shant Kumar, President of BIC and the BIC organization for inviting me to deliver this talk, and Dr. Kiran Kumar for agreeing to chair this, though they say in BIC they do not have a chair for the talks. I consider myself privileged to have him with us today because we'll talk about it later, but for today's India, modern telecommunication, which has made also IT possible, IT services possible, and modernized IT applications for India itself, two organizations contributed fundamentally. One was CDOT, which brought in the digital switch, which then digitized for the first time telephone network, and the other was ISRO. And normally we don't, we always talk about what happened in Silicon Valley, etc. But we don't recognize what the importance of these two organizations, which created the infrastructure, just like our institutes, IITs and other institutes, engineering colleges, and the professors there, so many of them, Professor Rajaraman, Mahavala, Professor Sanyal in Kharagpur, and so many others, who created the human infrastructure, the human resources, which made all these things, possible to take off. And so I'm sure after my presentation, he'll speak somewhat about what technologies ISRO itself developed to achieve what it has achieved today. We talk about drone technology, and we have a mobile phone or something, some controller, remote controller, and within a few minutes we say, oh, it has gone out of range. And just the moon is 400,000 kilometers away. And you are trying to move a robo there or trigger a rocket to fire or stop firing sitting here in Hassan or in Bangalore or somewhere where the master control facilities are. So you can imagine the kind of depth of technology which is required in all these things, modeling. And today if you see any failure in any space program anywhere in the world nowadays, whether it is Arianespace or ISRO or SpaceX or any of these, finally when the fault analysis committee comes up with the report, it will always say there is a software problem. So that is the amount of actually digital technology that goes into ISRO and its work. So I hope we'll get a flavor of that. And I'm happy that he made himself available for this talk. Today, now first let me explain a little bit about this topic, the title. Normally, this talk I have given in several IITs, several other colleges, and TFR, IIC, etc., NIAS, but the title would be different. It used to be Indian Contribution to Digital Technology. And the director of IIT Roorkee told me, no. Half the students will not even think of coming to the auditorium. Make this something like this. How Indians won the Silicon Valley. Okay? Make it, you're done marketing for TCS, then why don't you, apply it here? So very hesitatingly I accepted it, but then, so that is a caveat. First of all, let me just explain, though these are all very common terms, that Silicon Valley is not a geography, it's an idea. It is connected with all innovation, connected with silicon, that is digital technology, anywhere in the world. And even in the United States, when we say Silicon Valley, we also cover everything from Boston, Massachusetts, Route 81, to New York, Washington area, Atlanta, Dallas area, and then the Bay Area and other areas, up to Seattle. So literally it's a full parikramana of United States, that if you really want to chase where high-tech work is being done, Of course, the Midwest people might complain that we are being left out of this. But anyway, that is one small part, that when we talk about Silicon Valley, basically we are talking about all innovation regarding silicon. Of course, in the US, but now we are in a integrated global world. So no discovery, no innovation is local or can be ascribed to a single individual or single institution. Thousands of people get involved into it immediately within seconds, and sometimes without knowing each other, they will be working on the same issue and might have come out with similar innovations. And the moment they come to know about it, they network, and there is co-engineering, and all sorts of cooperation happens, and also rivalry happens. That is how today we can say Bangalore and Pune and Hyderabad and Mumbai and Gurgaon and Chennai and all these centers are also equally involved in the global innovation ecosystem. Now, other thing is the past tense won, right? Nobody won anything. There is no competition, there is no race which was won. It is just to say that Indians have contributed, and not only contributed but also made significant seminal contributions. So that has been recognized. That has been recognized by all the people within the industry and all that. Many people are not aware of it in India itself. And so I would like to describe some of those contributions. And before I get into those few examples, because instead of theorizing and making a big narrative framework, what I'll do is I'll just talk a little bit about pre-modern India or ancient medieval India and how those ideas have shaped today's digital technology. And then I'll go into examples rather than any kind of theoretical framework of few people. So obviously there is a limited time. Even if I talk about 35, 40 people for 2 minutes each, it's 1.5 hours, and that's all the time I have. So I'll briefly talk about what some 30, 35 people have done and what is their story. And there I'll end it and hand it over to Dr. Kiran Kumar. So now how I got into this, when I was working as a business journalist in Business India, our publisher said that, we have only heard about, this was year 2000, we have only heard about 2-3 individuals, one Sabir Bhatia, some Kanwal Rekhi, Vinod Khosla, etc. And that too, they were featured in Fortune magazine in a special report called Indian Mafia in the Valley. Okay? So he said, I'm sure there are many more than that. So he sent 4 of us, including a photographer, for a month to travel all over the United States and identify those Indians who had done very well as tech entrepreneurs. Okay? So that's why the title, Indians at USA, How the High-Tech Indians Won the Valley. And it was surprising to many that we actually found and profiled over 70 people. Okay, not 3, 4, 5 people, and spread all over United States, and who had done very well. So after that, there was a very good response to that, and one response came from some senior executive in Tata's, and he said, oh, these are all nice and feel-good stories, but what about fundamental contribution to technology and economy? So I said it's a valid question, and it took me a little time to realize now let me hook him, since he has made this comment. So I made a project proposal to them, to the Tatas themselves, saying this is my idea, but this will need support to research and find out how this technology has evolved since the birth of transistor in 1948, and what Indians have done in that global evolutionary history of this technology. How do we situate Indian work? And by Indians in India, Indians in the United States, Canada, and so on. After a lot of due diligence and all that, the Tatas agreed to support it, and then were very generously supported it. And as a result of that, I was able to, I took a sabbatical from Business India for about 1.5 years and interviewed about 300 technologists in academia, in industry, etc., in India, in US and Canada. And then there were a lot of plans, but one definitely was to produce a book for lay people to explain this whole story. So the result was a book I wrote called Sand to Silicon. This is a paperback edition of that. And now I have put it up on the internet. That is the URL. You can download freely from that. It may be available in a couple of other things also, because anyway, the print edition is, I think it's probably out of print. Those who are interested, a lot of what I'm talking about is either hinted there or probably some things explained in more detail there. And it is aimed at anybody who is interested in science and technology from, let's say, 12th standard level onwards. So everybody will get something from it, because I found that even MTechs and PhD in computer science and electrical engineering have learned something from it. That's what they tell me. Okay. Now, let me go to the foundations, where I'll talk about Indian contribution in the pre-modern era. The first thing, of course, is zero. Okay? So we all know about it, but we do not understand its significance many times. And some people look at it philosophically, etc. There is a philosophical element to it. But zero and the decimal system created by Indians totally turned counting, that is arithmetic, fundamentally. And one of the persons who candidly acknowledged it was Pierre Laplace. And you might know Pierre Laplace is considered one of the 20 greatest ever mathematicians that has lived. So main thing is the place value system of numbering, which Indians developed. That is, if you say 123, the 1, 2, 3, 1, 2, and 3 are digits. Each one has value 1, 2, and 3. But if you write it as 123, then 1 has a value 100, 2 has a value 20, and 3 has a value 3. So this is actually, if you are mathematically oriented, then this is a way of representing a number with the coefficients of a polynomial to the base 10. Okay, 1 into 10 to the power 2, 2 into the 10 to the power 1, and 3 into 10 to the power 0. Okay, and this and the carry over, because of the 0 you could carry over, that revolutionized addition and hence everything else. And some of you might know all that the computer does is addition. Even multiplication for it is an addition. So if we were to multiply 53 by 55, then it will add 53 55 times. But it does it so fast that it comes in milliseconds, right? So this is what Pierre Laplace said. It said, it is Hindus that gave us the ingenious method of expressing all numbers by means of 10 symbols, each symbol receiving a value of position as well as an absolute value. An important and profound idea which appears so simple that we ignore its true merit. Okay, then this is another totally different aspect of the Indian philosophical tradition that also revolutionized, you can say, logic. Because the logic that Aristotle developed, which we today know as binary logic, believes that every question has only two answers, true or false. And hence, in binary logic, when we implement that, we say 0, 1, right? And that's how the Boolean, we use the Boolean system, etc., to represent numbers and all that. But we know that not all questions, and in fact, very few questions you can answer definitively that it's true or false. Large number of questions in life, and any question anybody can ask, including a child, do not have true or false answers. So they are somewhere between true and false. That is, they are not black and white, they are all shades of gray. Right? So how do you talk about shades of gray in logic? And that kind of thinking was put forward by Jain philosophers, Buddhist philosophers. Buddhists developed a logic called Chatushkoti with 4-valued logic. Jains developed a 7-valued logic called Saptabhangi, and Shyadvad, based on Shyadvad. And these were fundamentally new things. And in fact, they were, you can say, curiosities for Westerners. Till Lotfi Zadeh in Berkeley University developed fuzzy logic influenced by these kind of systems. And in fuzzy logic, the answers are between 0 and 1. So that is what it is. That is the fuzziness. And in real life, you know that all your washing machines and microwaves and TVs are now using fuzzy logic, right? And not only that, before the talk of artificial intelligence and all that in the weapon systems, earlier in the 80s and 90s, many of the weapon systems were started using fuzzy controls, adaptive controls. Anyway, now other thing is extending the Ganita tradition, the counting arithmetical tradition. Aryabhatta and Brahmagupta and Bhaskara, the first Bhaskara, who was a contemporary of Brahmagupta, they, today, we all acknowledge them as great mathematicians. But what was great about them as far as people not familiar with the Indian tradition are concerned is how do you arrive at a solution? And if you have an algebraic type of problem where there are some unknowns, not everything is known. So arithmetic talks about knowns, right? 2 into 2 is 4, 2 into 6 is 12, etc. So all the 3 things are known. We call them constants, right? Digits. And then you can get into other kinds of numbers and all that. And with 0 you can talk about negative numbers, etc. But what about when there are unknowns? Now how do you find that unknown? And every school student now knows that there is something called an equation, and there is a right-hand side and a left-hand side. Then you transfer from right-hand side to left-hand side, etc. And then what is remaining, you figure out what that x is or y is, etc. Right? But this method was precisely what these people had developed. One of the things they contributed. And second thing they contributed was, how do you arrive at the solution of a problem? That is, how do you systematically arrive at the solution of a problem, even when certain variables change? The problem is the same, some variables might change. So that is step-by-step approach to come to the final result. And you might have to sometimes go back and do it till you get the correct result, to the correct accuracy that you want. These are, you can say, from theoretical point of view. I am not talking about whether they did partial fractions and this and that and the other things, but I am talking about from the theoretical mathematical point of view. These were 2 fundamental contributions by them, and this was recognized by Arab mathematicians. And one great Arab mathematician, his name was Al-Khwarizmi. He came from Khwarizm in Persia, and he studied Aryabhatta and Brahmagupta, and he wrote 2 books. And unlike many other authors, generally speaking, Arabs were very, they gave credit to the source. If they learned something from the Greeks, they said, we learned it from the Greeks. If they learned something from the Indians, they said, we give credit to the Hindus. So, Al-Khwarizmi, in his books, actually said, I learned this from Aryabhatta and Brahmagupta. Okay? And one of these books was Al-Kitab Al-Mukhtasar Fi Hisab Al-Jabr Wal-Muqabala. So, basically it means this issue of balancing the 2 sides, right-hand side and left-hand side. That is a method of solving certain algebraic equations, which he learned from that. And when this was translated into Latin, after the Crusades, I think, they took this word algebra and called this algebra. And the method of arriving at the solution, systematic method, step-by-step method of arriving at the solution, they called it Al-Khwarizmi's method. Though Al-Khwarizmi had said this is Aryabhatta and Brahmagupta's method. Okay? So the Latin version of Al-Khwarizmi's method was algorithmus, and today we call it algorithm. So every other day, every computer science student and practitioner at least, if it was some god's name, they would have got God by now. So hundreds of times they will say algorithm, 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 right? That comes from Al-Khwarizmi, and that comes from Aryabhatta and Brahmagupta. Then another very important thing which has great relevance to today's computing is the work done by Madhava, Nilakantha Somayaji and Jeshtadeva. They were all located in Kerala. As you can see, they're in different time periods. And they were able to express certain complicated solutions to complicated questions in the form of an infinite series. So, expressing something complicated in an infinite series and proposing methods to sum this infinite series. Sometimes you can sum an infinite series, and sometimes you cannot sum it. So, if it is giving a result, then you say, okay, the result should be good to 2 decimal places. For example, suppose you are calculating pi, right? Every child says, okay, circumference by diameter 22 by 7, and they say 3.14, right? So if it is 2 decimal places, it is 3.14. But if it is 3 decimal places, it is something else, and so on, okay? And it is rounded off to 3.14, right? So this, first of all, expressing certain things, certain functions, like for example sine, cosine, tan, arctan, etc., which were important for astronomy and positioning. Today we talk about global positioning systems, right? And where using celestial objects, stars particularly, and the position of the stars, the angle they make with the azimuth, etc., based on that you find your own latitude and longitude. And this was essential for oceanic navigation. And interestingly, Europeans didn't know anything about this. So Vasco da Gama floundered and he came, finally he landed up, I think, somewhere near Madagascar, and some Indian or African, they say dark-skinned person guided him to the coast of India. Okay? And they were already, the result of the work of these people was that some of these calculations could be done, and actually they have found in Lakshadweep some remnants of some of the instruments that were used probably for these calculations. Okay, these navigational aids looking at certain stars and so on. That is a practical application. But theoretically, that you can have infinite series, and you can sum certain infinite series, and you can cut off, if you cannot sum it, you can cut off depending on what is the accuracy you want. Do you want pi to the 10 decimal place? You can produce it. You want 100 decimal place also, you can produce it. You just have to take, much longer calculations and more terms in that infinite series, right? And this is exactly what you do in computational methods, in numerical methods. Because, whether you're calculating any orbit or any such thing, you're finding most of these equations, you need to solve differential equations, what are called differential equations in mathematics. Now, very few differential equations have analytical solutions, which come out neatly in the form of a function. So then you'll have to apply numerical methods and say, okay, I don't get a smooth curve, but let me calculate the value of the function here, 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 here. And then if you join the dots, you get more or less the function. Okay, that curve which represents the function. Okay, so all the calculations that you do of difficult problems in quantum mechanics, classical mechanics, celestial mechanics, you're calculating orbits, so many things, that finally one thing is you have to do approximations. So that means you have to see what is the model you are taking. You can't solve the real life problem, so you approximate it with certain which can be solvable, and even that you do it approximately. Okay, so that is called zeroism. That is basically, if it is 3.14159, then you say it is 3.14. And you say 3.1, 14159, so you can say 3.142 if you want third decimal place. Or if you say 3.14159, then you can say instead of 59 you make it 160, right? 59 is almost equal to 160. So there is a small error, and you can you ignore that to get stop somewhere and get some meaningful number. So that method is continuously used in all numerical methods and approximations that you do in computer calculations. So these are some things, some methods, some ways of solving problems, some concepts that we can talk about contributed by Indians. And here I would like to say that when we talk about ideas, whether they are philosophical ideas or technological, mathematical ideas, etc., it is very, very difficult to locate where it originated from, or how it was transmitted, how it diffused to other regions. So it is a futile attempt to say, so and so did this. Not only now, today we can definitely say that. We cannot say, when somebody says he's a father of this, he's a father of that, you can say mostly it's a hype. There is no single father of any technology today. There are thousands of people working together and all contributing ideas and leading to a successful technology, which again within 3 years becomes obsolete and something new has to be worked on, right? But even in the ancient world, it's very difficult to find out whether this thing originated in China, in India, in Greece, in Persia, or in Latin America, because they talk about Mayans knowing about zero and so on and so forth, right? So please, let's not fall into this jingoism ever saying that this is what Indians did and this is Indian contribution and Indians did it first and so on. Because we have seen enough of that done by the Europeans earlier. Because the earlier whole history of science, if you look at it, everybody thought and it was projected that everything came from, all modern science came from Europe, right? So from that Eurocentric version, which is now discarded by all modern historians, you should not get into an Indo-centric version or an Indic version saying everything came from India or this idea definitely came from India and so on. There is no basis for many of these observations. Okay, now let's come to 20th century. But before we go to 20th century, we'll have to start at 19th century. And you'll be surprised. The topic I'm talking about, say I'm going to look at various aspects of digital technology, semiconductor devices, chips technology, telecom, computing, internet, and in all these areas, I'll try to identify some individuals who made outstanding contributions and briefly tell what was that contribution. So I'll start with semiconductor devices because it is semiconductors which led to transistor, and transistor which enabled a digital technology, though they tried to use triode valves and all that earlier, but there were grave problems with that. They used to consume a lot of power and also produce a lot of heat. So the very first computer, which was built by von Neumann in Princeton, used to have huge, first of all it occupied a whole, building, and they had huge fans to blow the heat away, all the hot air away. And again and again those valves will fail. Okay, valves are like, you can almost say like incandescent bulbs, the old bulbs, which we don't see anymore, right? Where a small element is heated, and we are looking at bulbs for light, but in the valves, the bulbs are the source of electrons, and they emit electrons, and then those electrons are guided and so on, and so it leads to a diode effect, triode effect, etc. And they are used as elements. If you remember, any of you, if you have not seen it, I'm sure your fathers and grandfathers had these valve radios. The first radios were valve radios, right? You had these things which were glowing if you opened it, and many times they used to get burnt and all that. So valves never led to a stable, you could implement a digital technology, digital logic in the circuit based on valves, but they were not stable, they were consuming too much power and producing too much heat. So the first real you can say, device which enabled implementation of digital logic and all that was a semiconductor device which was called a transistor. This was done in Bell Labs in 1948, and many people talk about forecasting technology and what will this technology do and don't do and all that. Now, sometimes people, many times when I give talks, people ask me, oh, what about this, what about that, how will that affect this, how will ChatGPT affect this, or how will artificial intelligence affect that, and so on. I tell them very simply, boss, I'm not into forecasting, I'm a reporter, I'll report on what is happening on the ground. And I can't tell you what's going to happen 10 years later, 20 years later, because most such forecasts have been proved to be wrong. And one such forecast was made by the Bell Labs on transistor itself. When he was asked in the press conference in New York when they presented the transistor, what is its use? He said maybe it will be useful in hearing aids. Okay, and now we know transistor is the basis of all semiconductor devices and chips, etc., right? So he could not have thought of it. Same thing happened with the chip. The person who invented the chip, Jack Kilby, in Texas Instruments in 1958, I happened to be in Dallas when he had just received the Nobel Prize in Physics. He was given a Nobel Prize in Physics for an engineering problem he had solved because it had affected our life so much that Nobel Committee decided to give him a Physics Nobel Prize. So I was one of the first journalists to interview him. And he said when the chip was made and Texas Instruments people were happy, and then they said, what can we use it for? Then he said, okay, I can make a calculator out of it. So one of the first products from a 4-bit calculator, then 8-bit calculator, that was the first application of that chip. And many of you, you may not remember because you're all much younger than me, that when in engineering, the prized possession of an engineering student was a Texas Instruments calculator. And then later various other Japanese and Korean models came in, right? So the first person who actually saw this revolution happening actually belonged to the 19th century and happened to be an Indian. That was Jagdish Chandra Bose. All of us think about Jagdish Chandra Bose as a person who talked about plants, that plants can feel, okay? Plants might have a nervous system. Plants might have a system of communicating with each other, and so on and so forth, right? That is true. That is also his contribution. But in fact, his major contribution is in today what we call microwave engineering. So he actually demonstrated how to broadcast, how to produce radio waves, which after Maxwell had predicted radio waves, Hertz had shown that. But then he actually created a device to produce it and to receive it. And that receiver technology involved today what we call today as semiconductors. Okay? And he demonstrated it in Calcutta, then he went to London and demonstrated there to Royal Society, etc. And then venture capitalists are nothing new, okay? You might think it came from Silicon Valley. No, even in 19th century, all this happened in 1890s. That some businessman caught him in his hotel in London and said, you have to patent this, whatever you have invented this. And he didn't understand what for and all that, and he was not agreeing. Finally agreed. So the first ever patent on a solid-state device is taken out by Jagdish Chandra Bose. And it was these devices which were finally put together by Marconi and made a radio, but Marconi got Nobel Prize, not Jagdish Chandra Bose. But today IEEE recognizes finally what was contribution of Jagdish Chandra Bose. Okay, now I'll just talk to some others who have also worked in semiconductors. So this is not a chronological story. This is Jayant Baliga from, in fact, Bangalore, who studied in IIT Madras. And when he was working in IBM, General Electric Research in Schenectady, in New York State, he worked on a different type of a transistor. Now, if you look at chip industry and related to computers, etc., constantly we are trying to create smaller and smaller transistors, right? From first chip, of course, was about this big. There is a photograph of that, which was made by Kilby. okay, with germanium and gold wires and all that, okay, which was an amplifier he created with that transistor. But more and more, we're trying to create smaller and smaller, micron level. That is, micrometer is 10 to the minus 6 meter. I mean, you want to know what is a micron, you take a human hair. It is anywhere between 40 microns to 80 microns in diameter. So imagine going to micron level, and 1,000th of a micron level, that is called a nanometer. So today we are in the nanometer range, 2 nanometers, 4 nanometers, etc. Okay? So we are trying to create smaller and smaller transistors for various reasons. One is, smaller the transistor, it will consume less power. Right? So all the time we complain, right? Oh, my battery went off in my mobile. I wish I had a bigger battery, or a battery which will last the whole day, not every few hours I have to charge it. So which means actually your circuit is consuming a lot of power, right? So you try to minimize power. So one of the results of miniaturization of transistors is less consumption of power. And second thing is, this power, what happens to this power? Once, when it is circulating in the circuit, it produces heat. Okay, that's how we heat water, right? In a water heater, actually there is electricity going in a wire, and the wire gets heated up, and that heats up the water. So similarly, even the milliamperes and microamperes of current which are going in those chip circuits will produce heat. That heat, you have to do something about it. Just like the triode valves and diode valves produced heat in Princeton in 1940s during the World War II, because that computer was basically used for the research on the atomic bomb. That this is a big problem, power. So you also want to reduce power consumption and heat production and heat dissipation. So all these are very important parts of the circuit design and in the chip industry itself. But not all transistors, but we also need large currents. After all, in this residential area, we use 5 amperes, sometimes we use 16 amperes, maybe some applications we use 32 amperes and so on, high power devices. And AC may be consuming 16 or 20 amperes. So you need circuits, you need controls, because transistors are used basically in controls. So controls should be able to handle large currents. Now if you take a bullet train, a Shinkansen, then you will have to handle thousands of amperes and sometimes a million amperes. So you need to create transistors which can handle large currents. They are called power transistors. And Jayant Baliga worked on one such thing. It was called IGBT, Integrated Gate Bipolar Transistor. And it led, after a few years, that was it led to a multi-billion-dollar industry now. And it's not just in Shinkansen, in bullet trains. We have seen ourselves, or we see it in all these serials, television serials, in the hospital, related to hospitals, etc. When somebody has a heart attack and they're trying to revive him, they give him a shock, right? And those pads or paddles which are used to give shock, that whole system is called a defibrillator. Again, these transistors are used in those defibrillators. So this is another major contribution in the power transistor sector, but at the same time extremely useful. This is Umesh Mishra, young person from IIT Kanpur. Now he is in Santa Barbara, and he has been working on you can say relatively new semiconductor called gallium nitride, and he has done excellent work in that. And today, by the way, gallium nitride, we should also recognize that because we are using for the first time LEDs, right, for lighting. The old LEDs produce red light or yellow light. The white light producing or blue light producing LEDs use gallium nitride. And that work was done by Japanese scientist for which they were given a Nobel Prize. He's also working in gallium nitride, but his work affects various applications in defense and even in mobile telephony. All these base stations, the towers through which mobile telephony, your call is handed over and so on, they use these gallium nitride high frequency transistors. Okay, now let's look at the chips, microelectronics and chip industry. One of the early entrants into that is Pallab Chatterjee. And recently has been coming a lot to India and Bangalore and all that. He started his career, he's from IIT Kharagpur. He started his career in Texas Instruments and did a lot of work for which he received all sorts of honors in developing the chip technology. And then not only that, in the 80s, the Americans suddenly found the Japanese chip industry is going far ahead of them. They're producing cheaper and more powerful chips. So, US government got worried about it. So White House appointed a committee to investigate what is it that the Japanese are doing which is leading to this success for them, and what is it that means, what is it that we need to do in America. And obviously these are all industrial secrets, and no Japanese, Toshiba, Geshiba, nobody will allow you into their actual chip manufacturing plant, and especially if you're an American, right? So the committee consisted of Pallab Chatterjee and another, an Indian, an academic from Stanford University, Krishna Saraswat. So these two people wrote a report. They figured out what was it that the Japanese were doing and which led to their success, relative success. And that again, when the American semiconductor industry implemented that, America also started making much faster progress. I don't have the time to explain what actually they found and all that. Maybe if there is some time later, we'll do that. Okay. Then Vinod Dham, you have heard of his name because he is generally promoted as father of Pentium and all that. Basically, he was general manager of the project in Intel, which actually developed, produced, and the Pentium chip. And till recently, Pentium chip has been the highest selling chip from Intel. And he studied in Delhi College of Engineering. The Atiq Raza, he's from Lahore, Pakistan, and great technologist. He was literally driven out of Pakistan during Ziaul Haq's years because of his liberal and reformist views. So he landed up in Silicon Valley, great friend of India and Indians. And in fact, he has helped a lot of Indians in the industry also. And it was his team and his technology, you can say, which led to a period when actually Intel was challenged by AMD. AMD was another also-ran, it used to be an also-ran company. But the technology brought by his company, which was called NextGen, the NextGen was acquired by AMD, which led to all the changes that AMD did. And recently he was telling me that actually it is core his team, which is now in NVIDIA, is what is leading to all this big jump in NVIDIA's artificial intelligence supporting chips. And today NVIDIA has become, nearly $1 trillion company, I think, in market capitalization. Suddenly it has grown like anything. Anyway, he also has links, by the way, with Bangalore. When he started an incubator called Raza Foundry, I think. He started it, one of its branches was in, other than Silicon Valley, was in Bangalore. Okay, now I'm going to talk about 3-4 individuals who did some remarkable work. Suhas Patil from IIT Kharagpur, later MIT. Prabhu Goyal from Suhas Patil is from Kharagpur, yeah, and Goyal is from Kanpur. Then later, I think he went to Carnegie Mellon and then joined IBM. And Rajveer Singh from Roorkee Engineering College, then worked in TIFR and so on, and then later he went there. Yeah, these, Okay, these 3 individuals, they did something remarkable, which has actually affected us today, affected us business-wise. And that is, you see, Ravi Shankar plays beautiful sitar, right? all of us know that. Produces beautiful music. But he doesn't make the sitar. Right? So sitar is the hardware and Ravi Shankar's music is the software. So in musical instruments, at least in the modern era, the distinction is separate, is clear. There are people who make musical instruments, wonderful musical instruments, and there are people who play them and produce this wonderful music. Right? This separation took a long time. If you look at medieval sants and fakirs and all that, bhaktas and all that, who used to also sometimes sing while traveling or wherever they are, ektari, kinnari, etc. They used to make them and then play them and sing along with them. Okay? So, chip industry till you can say 80s was in that stage, where the people who designed the functions of the chip also were electrical engineers who designed the circuits and then actually got involved in creating those chips, in the fabricate those chips and so on. So the hardware, that is chip making part, fabrication part and design part were merged. Okay? But it is people like this, Rajveer Singh, Prabhu Goyal, Suhas Patil, etc., and others also, non-Indians, they played a major role in separating the two, the design and fabrication. So today you can have engineers sitting in, Intel engineers, TI engineers sitting in Bangalore or in Hyderabad, Pune, whatever, Bombay, Delhi, and designing the most advanced chips without ever having seen an actual fabrication plant. And the fabrication plants can be in Korea or mainland China or Taiwan, wherever. So this bifurcation actually not only increased the power of the chips and the overall this division of labor, clear-cut division of labor, there is one design and test element and there is a fabrication element, was that was a big leap for the chip industry. And these Indians played a major role, stellar role in that. Rajveer Singh, Prabhu Goyal, Suhas Patil. Now, okay, Vinod Khosla, everybody knows today as a big venture capitalist from Silicon Valley, etc., right? But actually, he got into computer, and he is the founder of one of the great computer companies at one time called Sun Microsystems. He and three others, all Stanford graduates, Stanford Business School graduates, and so on, who were also engineers, who started Sun Micro, and which was a great company at one time. Now, of course, it doesn't exist. I think it's now part of Oracle or something like that, right? But Vinod Khosla actually started, his intention was not to start a computer company. He actually wanted to design chips. So he started a company called Daisy Systems, which was interested in creating precisely the kind of software we are talking about to design chips. But then he said, you want to do these things, to develop these packages and test them out, etc., these design packages, you need a powerful computer. And those computers, or what were called workstations, didn't exist. So he started Sun Microsystems. Anyway, today is a very major venture capitalist who has funded lots of companies which have changed the internet economy, internet technology, etc. Janak Patel, he's from MS University, Baroda. He's now in University of Illinois at Urbana-Champaign. And he developed an algorithm which can find out whether a chip will work or not. It's a testing algorithm. Okay? It's very important that whatever chip you have designed should work. Because without checking that, you just go to the fab and make it. Maybe you'll have to throw away 50% or 70% of the chips because they're not providing that function when you test them. So before you take it to the fab, you have to test your design. Is it going to deliver that function or not? And his algorithms enabled that. So every chip making company, Intel, Motorola, etc., started using his algorithms. So you can say he's a software engineer or a computer engineer who is not involved in the chip industry, but who is able to figure out how to do these tests. Okay, now I'm going to talk about 2-3 people who produce new technology by combining psychology with technology. Because there is a limit to innovation when you only stick to mathematics and electrical engineering, signal processing, etc. They found that. Whether it is signal compression, particularly signal compression. Okay. So, in various sectors, actually they had to utilize how humans perceive this, how humans perceive sound, how humans perceive, color or a picture, and accordingly keep that information which is important to human eye and human ear and throw away the rest. So that naturally leads to compression because you're throwing away so much of the signal. Okay. So, of course, the doyen among them is Amar Bose. All of you have heard of him. He's a speaker, etc. Strictly speaking, he's not an Indian. He had an Indian father and an American mother. His father was actually a revolutionary, Noni Gopal Bose, in Bengal. And British CID were chasing him, so he jumped into a ship which went to America. And there he settled down, started a small radio repair shop, etc. And he married an American. And Amar Bose was her son, and brilliant engineer. From poverty, he went straight into MIT and did brilliant work there with Norbert Wiener, who was one of the great mathematician engineers. And he also came to India. He spent a year in India after his PhD as a postdoc, because Norbert Wiener was a friend of India. He said, go to India and spend some time, before you take a faculty position. So he spent some 6 months with Malnobis in Calcutta and 6 months with Krishnan in Delhi in National Physical Laboratory and so on, where in this period he told me that he refined his ideas about audio, because he was a music lover, he was a good musician also. And he said that, those days the new thing in music was hi-fi. Okay? Today anything fashionable we say hi-fi, right? But hi-fi actually means high fidelity. So high fidelity to the original, that is original sound. So if you reproduce the original sound as it is, then you can call it high fidelity. If you distort it, that is what you call distortion, right? And most audio reproduction is distorted. So you get one experience in a concert hall, but you get a different experience in your living room or whatever. Okay, wherever your sound system is. It could be in your car. So how do you recreate the concert hall experience in a car or in a living room? And only Bose speakers do that. Because Bose cracked that. And he cracked it by studying what is called psychophysics. And he developed a course in psychoacoustics because he remained a professor in MIT for 40 years while also starting a company on the side. And actually he proved that a professor can not only teach but can also innovate and also start a business on the side. And MIT allowed him to do that at that time in early 1960. And that revolutionized audio. His speakers and all the real rigorous mathematical work he had done. But along with the mathematical work, he used what was called psychoacoustics. And he gave a course on psychoacoustics in MIT. And people say that course was so brilliantly delivered that in the huge lecture hall in MIT, there was no standing space for his lectures. And year on year, he is one of the most popular things. Also, Bose was a great friend of India and used to ask about India. He told me how he was a child, and in his childhood, his father, though he went to the United States, never left his contact with the revolutionary movement. And there were some revolutionaries from India who were escaping to America and so on. And some of them used to come and they used to talk, in whispering tones on the dining table when he's sleeping, half asleep, and he will hear some of those things. Jallianwala Bagh mein hua, idhar udhar ye hua, and all that sort of thing. Anyway, this is Arun Netrawali, actually originally from Karwar in Karnataka. His family moved to Mumbai, and they were not well off. So he studied actually in a municipal school in Mumbai. Okay, not any fancy school or a convent. And then he was bright enough that he got into IIT Bombay, and he did very well in electrical engineering. and later went abroad and did his PhD, and later he landed in Bell Labs. Because Bell Labs at that time was the place to do all sorts of research, which was, it was attached to an industry, but you could do, quite research which could be useful to industry and sometimes may not be useful to industry at all. For example, the people who discovered the microwave background radiation in cosmos, which finally led to the confirmation of Big Bang theory, were also from Bell Labs. Okay, so anyway, his team, he worked a lot on the standards, in JPEG standards, MPEG standards, and so on. And it is his team which created high definition TV. Today we have all our TVs are HD TV. So his team which created high definition TV. And he first demonstrated in Los Angeles Olympics in 1984. Right? Nobody remembers that. It's just a historical fact. If at all we remember Los Angeles Olympics, it is because of Carl Lewis and his 4 gold medals, right? But or P.T. Usha missing it by a millisecond, right? But his team demonstrated that you can produce very high definition, very sharp pictures with this new technology, which used again lot of stuff from psychology, what are called perception studies. Okay. I'll explain that in the next case, which actually this is N Giant. N stands for Nuggehalli, which is a small village near Mysore. Okay, he did his PhD in IISc here in Bangalore, and he also landed up in Bell Labs, and it is his team which produced MP3. He was in signal processing. And actually the principle that he explained to me, which he's doing in this photograph, is that what they found, again, they had done their limits using mathematics and electrical engineering and normal signal processing, okay, whatever it is, PCM, all those, whatever sampling they had done and all that, okay, of the signal and to compress it. But then they found that what about the human ear? Then they found that only in a sound, only the ear is receptive or responsive only to 10% of the frequencies. 90% of the frequencies actually don't affect the ear. That discovery was a great discovery. So they developed the algorithms to identify that 90% and throw it out. So immediately that led to 10 times the compression, whatever you had achieved before. So suddenly, what it needed as CD, you could send through a telephone line, right? So now everything is MP3, all audio is in MP3, right? And you can get concert type music with a very small bandwidth even, right? Okay, now I'll talk a little bit about another infrastructure area without which you don't have any data communication or this thing. Oh, I'm almost, I have another half an hour. Okay, I'll rush through this. This is another great man, Narendra Singh Kapani. He is a true, you can say, father of fiber optics. Okay, one of the few people who can say father of fiber optics. He is a boy from Dehradun who studied, his father was working in the ordnance factory there, and he studied in Dehradun, he did his BSc physics and all that. And he used to wonder, why should light travel only in straight line? Why can it not travel in a curved, line, curved pipe? Can we build pipes through which we can direct light? Okay, so it was just a, if you remember, I don't know, if you read Einstein's history, even Einstein at a high school level used to think about relative motion and how it affects his own image. If you are running with a mirror, will I see the same reflection or not, and so on, which later led to relativistic equations and theory, special relativity. So similarly, this boy was thinking about that, and maybe he was trying to construct it with prisms and all that. Prisms bend light, so maybe a system of prisms can bend light and so on. But he got an opportunity to go to London and work in Imperial College, initially for a diploma and later it became a PhD. And the person who is speaking there is his actual guide, Hopkins. Dr. Hopkins was his guide, and he told his guide that this is what I want to do. I want to see, can I make a fiber of glass and through which I can send light and it will appear on the other side. Okay. And it was good of Dr. Hopkins to encourage him to do that, because otherwise many times, you think, oh, crazy idea, you'll not achieve anything, forget about it, right? So he worked very hard, and he went there in 1951, and in 1954 he published a paper in Nature along with his guide on how he has achieved it, what he had to do, what all he had to do in that fiber to make sure that a reasonable amount of light which went inside it also came out. Because otherwise, if you take any glass piece and put light, it will get diffused and it will be lost. It might not come out of the end, right? And his idea was actually to use it for what all of us today go to the hospital and get done, endoscopy. His idea was to put a pipe inside your stomach or any other organ to see what is going on inside. Okay, but today we are seeing all scopies, laparoscopy, colonoscopy, endoscopy of various types. They all use fiber optic devices. Of course, they add a camera and etc. to it, light and all that to light it up. So it has become more complex. But that was his actual intention, to do that. And in 1960, Scientific American asked him to write an article about it, and that's where he coined the word fiber optics. There is an interesting story about him. I don't have time, but it's a very interesting story, so I'll just recount it. That after his PhD, he went to United States. I think he went to Rochester. Rochester was famous for optics at that time. Also, Kodak happened to be very close to Rochester campus. Then he went to New York because Maharaja of Patiala at that time, the senior Maharaja, Amrinder Singh's father, was heading the Indian mission in the UN. And so Maharaja of Patiala had come to New York. He was heading that mission. Some session was going on. So he just went to pay respects to him, and probably the family knew the Maharaja earlier. So the Maharaja was very happy to see this young man and talk to him. And Krishna Menon happened to be there, so he introduced him to Krishna Menon. And Krishna Menon, as usual, he made a joke. He said, oh, one Sardar was enough, now we have two of them and all that. Okay? And then he said, okay, young man, when you come to India, you visit me and all. You seem to be a bright guy, So just then he got married and came to India, and he wanted to take his wife for a honeymoon to Srinagar. So on the way in Delhi, he went and met Krishna Menon. And Krishna Menon apparently immediately fixed up a meeting with Pandit Nehru, that Nehru should meet this man, and Nehru gave him almost an hour and asked him all sorts of questions and tried to understand what work he was doing. At the end of it, he called the secretary who was looking after, at that time, public service, UPSC, and today I don't know whether it was called UPSC at that time or not, and said, write an appointment letter for him. He's going to come and head our defense research. That time it was not called DRDO. Later it was called DRDO. I think Professor Kothari, DC Kothari was heading it. Anyway, so he was going to retire, so they wanted a new chief. And then there was a science congress. They gave him the honor position, young man, to come and speak there right after Pandit Nehru, Homi Bhabha spoke there, and the third person to speak was this young, you can say postdoc, Narendra Singh Kapani. He recalled that, I have not published that interview of his, that all these things. Then he said, Prime Minister Nehru told him, go and wind up your things and come if you like this thing. So he liked it. He said, it's a good challenge and I'm coming back to India, I can contribute and all that. And then he waited and waited 6 months and the letter never arrived. So that shows what all bureaucracy can do. Even the Prime Minister has dictated a letter to that secretary, and that letter was never actually dispatched and sent to him. And then I think some communication came. By that time he had already settled down and he had other plans and all that. So India's loss was Silicon Valley's gain. And then of course he did a number of new things, including the first eye surgery using a laser. He did that in Stanford University Hospital in 1966. Just then Ruby laser was invented. Okay, now anyway, this is Desh Deshpande. Most Bangaloreans and Kannadigas know him since he's from Hubli. He did a lot of work in optical networking. using lasers to communicate large amount of data and all that. It's called dense wave division multiplexing, DWDM, and the kind of technologies he also started many companies, successful companies, which were very active in the optical networking area. Now, let me go to the internet. Abhay Bhushan from IIT Kanpur, after his BTech here, he went to MIT to do his master's, and this is 71 period. And at that time, you know, the big project, exciting project he found was that for the first time in United States, there was an organization called ARPA, ARPA, Advanced Research Project Agency. Later it was called DARPA, Defense Advanced Research Project Agency. It was headed by a brilliant psychologist, okay, not technologist, called John Licklider. Now Licklider was thinking, you know, how can we use this, big mainframes were there at that time, how to make use of these computers. So can we make computers talk to each other? You know, today we say networking, right? So the experiment was, so this, he funded that project. It was called, later it came to be known as ARPANET, a network funded by ARPA. And they're basically trying to link about 3 or 4 computers, one in MIT, one in Carnegie Mellon, one in UCLA, and one in Berkeley. Okay, and to see that messages go from one to another. The idea was that computer time is so expensive, computers are so expensive, since all the time this MIT computer is not being used, maybe can somebody sitting on the other end in San Francisco, can he link to this computer and use it for his research, right? That thing, resource sharing. Resource sharing is a very important thing, right? And we all do it. In India, one fellow buys a paper and 10 people read it, right? So see, fundamental ideas in technology, business, life, they are very few and very simple, and they have been there for a long time. They just keep coming in new names and all that. And later it led to time sharing. Today we might call it grid computing, cloud computing, all sorts of things. Okay, that how do you maximize, optimally utilize the expensive resources, right? So, by the way, what he did was, at that time, the technology was still getting developed. So you had to, if you are coming up with a new idea, you give a technical specifications of that and send using your communication, whatever file transfer you are doing, in whichever way, to all the people who are, that is basically these four campuses. So they're called RFC, request for comment. So he wrote an RFC for what we today call file transfer protocol, FTP. So that was the birth of email. That actually files can be transferred, which means a message can be transferred, etc., etc. Later, of course, a new protocol was developed called SMTP, which became more common in the email. So you can say he's probably the first fellow who thought of using computer networks for mail and messaging and so on. This is another IIT Kanpur product, Pradeep Sindhu. He went through various things, biomedical engineering, this, that, after electrical, then finally landed up in Silicon Valley from Hawaii, and there he came up with the idea. He saw that this new internet is coming. This was in the mid-90s. New internet is coming, but it's not using IP, internet protocol, so which will actually make this more robust, etc. So I will create routers using IP and which can route a large amount of data. And that idea was funded by Vinod Khosla, and that established a company called Juniper Networks. And the established company was Cisco. So he was bold enough to challenge Cisco, a small startup. But their idea was revolutionary, far ahead of what Cisco was doing. So it led to a new company coming, new player coming, establishing itself, and today a lot of internet infrastructure is actually made up by Juniper Networks. This is even earlier period. Another guy, Yogen Dalal from IIT Bombay. Very interesting that he as this BTech project, if there are some IIT Bombay people, I see some people here, they will remember that IIT Bombay had one old clunky Russian computer, right? And that is it. But there was a better computer in TIFR, a CDC computer. I think it was a CD6 3600 or 6600. So, but IIT Bombay is one end of Bombay and TIFR in Colaba is another end of Bombay. So he said, can I sit here and connect to TIFR computer? That is my BTech project. And there was one professor called Professor Isaac, okay, and who all IIT Bombay students would know from 70s and 80s. He was the head of the computer center and whatever, there was no, I think, no separate computer science department at that time, definitely. So he encouraged him. He said, okay, do it. Of course, like most BTech projects, it failed. It didn't work. But then he went to do his PhD in Stanford. And there, he and another graduate student called Carl Sanders and his guide, Winton Cerf, together came up with what we today call TCP/IP. Transfer Control Protocol, Internet Protocol. And that is a foundational protocol for Internet. Today, Internet is based on TCP/IP. Okay? And basic idea is, you see, there can be local networks. And each network may be involving different computers, different protocols, different types of systems and all that. But how do you connect this network with another network? And so it was looking almost impossible. And in Hawaii, they had developed a system called Aloha, because there you couldn't even have cables, everything had to be through wireless, because it's made up of so many islands, right? So, to connect all these diverse systems, you needed a new protocol, and that's what TCP/IP provided. And that is what internet means, inter-networks, right? Okay, now this much talked about artificial intelligence today, it's a very fashionable buzzword. So I'll talk a little bit about that. One of the first pioneers in artificial intelligence is Professor Narasimhan. He is a 40s vintage, by the way. So ideas of artificial intelligence are not new. In fact, the first conference on artificial intelligence was held in 1956 in Dartmouth College, where they finally produced a manifesto and said, this is the thing. Minsky, McCarthy, all these people were involved in that. And they produced a manifesto saying, these are our aims, this is what we think, we know how the brain works, and we can model it, and so we're going to do this for vision, this is for music, this is for brain games like chess, and so on, or natural language translation, machine translation, and so on. Okay. So anyway, his other very important achievement is Baba picked him up in the 51 or something. He came back to India after his PhD in mathematics, and Baba said that we want to build a digital computer, and you do it. Now, he had used digital computer for his mathematical work, but he didn't know anything about circuitry or digital circuitry or any such thing, or the components. And 4 other people were part of his team who had never even seen a computer. And these people started actually constructing from the ground about computers. And you know, those days, the only electronics knowledge that was there was probably in All India Radio. Right? They were using these transmitters, and they had these valves and this and that, so they knew how to deal with it. So there was no advanced electronics knowledge at that time. This is 51, 52, 53. So within 2 years, I think, they produced by 54 a digital computer. It was called TIFRAC, TIFR Advanced Computer. And at that time, it was as good as any other computer that was there in the world in terms of speed and various other things. Okay? So actually, it was a trial by fire for him, for a mathematician, to get into digital electronics and actually finally build a computer. And then later, through again another very interesting route, you know, Baba was studying cosmic rays and things like that. To study cosmic rays, they use different types of instruments. One of those instruments is called cloud chamber, where a cosmic ray which passes through this cloud, not cloud, actually this vapor, leads to condensation along its path because it ionizes that vapor. So then you take a picture, then you actually see the path of that picture. You actually take the picture of those droplets, right? Condensation. So that gives you the curve or the path of the particle which is coming as part of the cosmic ray. Then you put different electric fields, magnetic fields, and try to bend it, etc., and try to measure the charge or the energy in that particle, etc. So Baba gave me a problem. Suppose, we don't know from which direction the cosmic ray is coming and which direction it is turning, etc. So just we are taking two-dimensional pictures. From these pictures, can you make sense out of it and say this is actually coming from this, lead to more, which can lead to a better picture, projection of that, which then physicists can use their formula to calculate charge energy, charge to mass ratio, and so on, right? So what he did, his mathematical brain got into pattern recognition. So he was one of the pioneers in pattern recognition. This is Raj Reddy, a civil engineer from Madras. He went to Australia to, I think, did his master's again in civil engineering. Then he landed up in Stanford. And in Stanford in 1962 or 63, when he landed up there, you know what they were working on? They were working on what we today call Pathfinder. Pathfinder is a robo which is supposed to move on Martian surface. In 62, 63, Stanford was working on that. When they didn't even have a proper flight. That barely launched their first Sputnik and all that, and they're competing with Soviet Union. That time Stanford was working on what if we land on Mars, a robo, how will that vehicle, robotic vehicle, move around and how to control it, how to make it realize where is a stone and where is a ditch and how to go around it, etc., right? Computer vision, etc., and even controls and motion and all that. So that is how he got into artificial intelligence, starting with computer vision and later speech and all that. And he did wonderful work. And later, of course, like most pioneers in artificial intelligence, after 20, 30 years, all of them left artificial intelligence because they found that actually the fundamental problem was not computer science, but they didn't know enough about the brain. They thought they had understood how the brain works. Because in 1956, they had decided that brain works like a digital computer. And that's how they had made all these projections. And suddenly they found that no, digital computer is nowhere near what the brain does. And so we still don't know how the brain works and so on. So there was a big lull. Everybody, all the leading people worked in artificial intelligence left that field. And today there is a revival, but that's again not that we understand brain better, but we have more processing power, etc. Real-time processing we can do, number crunching we can do. That is a separate story. But Raj Reddy's contribution to robotics and artificial intelligence was recognized by all the computer scientists. And within computer science, there are a number of awards and prizes for leading work in computer science. And the highest award, the Nobel Prize in computer science, is considered Turing Award. Alan Turing is a British mathematician, engineer, whatever you call him, was one of the persons who established the idea of a computer. There is something called Church-Turing theorem and all that. Okay, so in his name, the ACM, the Association of Computers, computer manufacturers, but actually it is a highly academic body, and they give this Turing Award. And he is the only Indian who has received that. And he's still in Carnegie Mellon as, I don't know, emeritus, etc. Comes to Hyderabad often, is associated with IIT Hyderabad, IIIT Hyderabad, and so on. Arvind Joshi is no longer with us. He is again from Pune, and I don't actually remember where he studied, but then in India, but then he went to do PhD abroad, and he was one of the earliest people to get into machine translation. That means, can machines understand natural languages? We know that machines understand computer languages. That's why we call them computer languages, because whatever it is, basic, Fortran, COBOL, or all the modern, whatever new languages you have, right? the machines understand that, assembly language onwards. Right? But if you talk in Kannada or Tamil or Hindi or English or German, will the computer understand? Will do exactly what you tell it, and so on. Means, do you understand? So you have to first understand what is the structure of the language and what do you mean by understand. Right? All these things. So there is a lot of things involved in linguistics and analyzing languages and then seeing how to resolve many of the, because natural languages have ambiguities, right? Tremendous ambiguities, which a 1-year-old child can understand. If mother calls her 1-year-old child, come here, the child may obey it, may not obey it. Just by her tone it recognizes whether the mother is angry or mother is playful and all that, so it might decide to come scared or it might decide to ignore her. Right? So that sound, it processes the sound and understands with what intent the mother is calling. Then when the mother says, come here, it says it understands what here is. You can't tell a robot or a computer, come here. It will ask you GPS coordinates of here. Right? So here is ambiguous, but that child understands that. And there are any number of examples you can give from natural languages. One of the interesting, comic example is one guy was driving a nail into the wall, right? So, but he could not, so he was holding the nail and his friend is supposed to hit the hammer on the head of the nail. So he said, okay, when I nod, hit the head. Now he'll be lucky if the guy understood it and hit the head of the nail and not his head, right? So natural language has so many ambiguities, double meanings and so on and so forth. So machines want very clear instruction, right, left, aise karo, this sequence of the instructions and all that. That's why the great physicist Feynman, who gave fantastic lectures on computing in I think 80 or 81, Feynman lectures on computing are great. Because there he calls computers as stupid machines. Right? When everybody was glorifying computers, he said they are stupid machines because they cannot think. They'll tell exactly what you want it to do. Of course, they will do it repeated things very much faster, more efficient. They will not feel tired. Whatever human beings, those repeated functions, human beings get tired or get bored. The machine won't, and so on and so forth. But there also he put the seed for quantum computing in those lectures, which of course today is another buzzword and a fashionable thing. Now, coming back to Arvind Joshi, so he did fundamental work in what is today called computational linguistics or natural language processing. And when I met him 20 years ago and I talked to him, I said, what are you doing now? He said, we are observing 1-year-old and 2-year-old children. Okay, he was not doing mathematics, he was not doing, so he's trying to behaviorally understand how the child disambiguates, how it resolves his ambiguities, how it, starts, it's called first language acquisition. Okay, how does a first child acquires the first language and is able to understand normally it's a mother, so that's why we say mother tongue and so on, right? So anyway, so he did amazing work in natural language processing. Now, let me talk a little bit related to Indian IT industry. There are several other things, I'll try to rush through it, but this is something important. What is it that Indians have done which has given them a head up, that they are in the leading position in software development? Today we call it software services. So to describe that, first of all, software development, or what used to be called programming, right? Earlier days in the 60s and so on, mostly when the first computers came in and you had to, first languages were developed and all that, it was mostly engineers and scientists who understood that how to use it, and they tried to write down their problem which they want to solve in a computer language and fed it to the computer gave a result, right? And unfortunately, sometimes like when we were studying still in early 70s, it used to take 24 hours to get our result back. Not like today, immediately the computer tells you, right? It's right or wrong. That interactivity, that speed, that accessibility was not there. There was one big mainframe computer and so many people had to use it. So you give your program, it will process it, and it will give an output, and you go and collect it next day. And 90% of the time, the computer would have said syntax error, right? It couldn't execute. So you had to go back and read, you used to punch those cards and read each one of those cards and see where was a mistake and correct it and all that, then again feed it and wait another 24 hours, and so on, right? But anyway, the point is the process of programming was a single person's brain functioning. The problem was given to him, he will model it, he will work out what is called a flow chart, that means how to solve this problem, what are the stages. And he will write the program, the algorithm, to go from one, how to complete each one of those tasks and one after another, then finally reach the conclusion. Right? So, a brilliant programmer will write a brilliant program, which will do it very efficiently and this, that, and so many things. But then, each programmer will program it in his own style, with his own logic, with his own way. So many, some shortcut he has taken, you may not understand if you didn't know him or he didn't explain it to you. So, it was like an artisan's activity, right? A brilliant painter, or forget a painter, even a brilliant kumbar, a potter, makes a beautiful vase, right? So, but if you ask him to make 10,000 vases, he will definitely, none of those may be the same, right? Each one will be slightly different. So there is nothing called standardization. And what he is doing, what are the tricks he is using, right? It is just like grandmother's recipe. You might write it down and go and try it, but you will never get what the grandmother did, because that little secret recipe she won't tell you, right? Same thing with even music, right? Musicians, they will only to the great gurus will only teach their closest shishyas that what is that little thing about that gharana, which they will get, not to everybody, right? So that little thing, that mysterious, that magical ingredient is left out, right? So this is all brilliant, but you cannot make 10,000 of that, of the same quality, of the same shape, or same functionality, and so on. So that is why programming was an artisanal activity. But if you want to do complex problems, and moreover, this guy who has done that program, maybe it worked, and now he has left the job and gone. Nobody else will understand what he has done. And definitely, you cannot break a task to 2, 4, 10, 15 people and say, you do this part, you do this part, you do this part, but each one will do it differently. And if all those things have to be assembled together to build something, like a Lego, a Lego will never work if that thing is even different by 1 millimeter, that fitment. It is something very similar. So, that is called modularity. That is called componentization. That is division of labor. Okay, so all these are actually concepts from manufacturing. And this is what the great Henry Ford did to car manufacturing. People were manufacturing cars before Henry Ford. In and around Michigan, there was many people, they used to call them quadricycles. They will make these cars, maybe 3 or 4 cars in a month or so, maximum. So he said, I want to make 100 cars in a month. How can I do that? So he created the assembly line and all that, division of labor, not just division of labor, perfect components, and all those components should reach the right person at the right time. And the right component should be there. He is supposed to say, just all his job is to turn a screw or weld a spot, right? But if he gets a wrong size screw, then he cannot do anything about it. The whole assembly line will stop. So this will give rise to great productivity, but it needs huge organization, standardization, componentization, and modularity. Modularity means somebody has made this subsystem, somebody else has made this subsystem, and the two can talk to each other. When you bring them together, very easy to build the larger system. So same thing in the structure of the program. So all these things that bringing these concepts of industrialization or engineering, okay, from manufacturing into services and a service like programming. That is what the Indian companies achieved. That is what what is called software engineering. It's not programming. It is industrial activity, industrialization of programming. And so that whole methodology, the experience of that, the management of that, today we say project management, right? There are programmers, coders, and there are project managers, and so on. There are software architects, and so on. All these things, terms we have in the industry, right? So this was done in the 70s. Actually, Indian engineers in some of the pioneering companies participated in IEEE and even in the SREI, in the Software Institute in Carnegie Mellon, to set those standards and quality and so on, and later lead to all those qualifications, CMM level 4, level 5. Even in formulating all those things, these Indian engineers participated in that. So we have, that is what led to industrial activity, programming as an industrial activity. So 1,000 people can do solve a problem. And if you've got 10 problems, then maybe you need 10,000 people. And each, 1,000 people ka group bana ke, usko you need people who can break that, understand that problem, convert it into a programming from a business problem, you convert it into an engineering problem, and then break it into pieces. Then you create all those standards of quality and standards of programming, standards of language, etc. So that again, at each stage you can check the quality so that it works. So testing, everything. This whole, thing was developed in the 70s and 80s, you can say. So that is the advantage, is what, that is a human resource that we have developed in large scale. It's not some academic institute, some university or some IIT. Today we have lakhs, right? I mean, Tata Consultancy has some 6.5 lakh engineers. Can you imagine that? Entire Indian Railway has about 11 lakh people. 6.5 lakh engineers. Then there are other companies, Wipro, Infosys, HCL, Tech Mahindra, each one has 2 lakh, 3 lakh engineers. Totally we have today about 40 lakh engineers working in software engineering, in software companies. And the biggest, China produces more computer engineers per year than India. And the biggest software company, software development company, I am not talking about some e-commerce company and this and that. A software services company in China, the biggest one has 30,000 engineers. They want to learn. They want to learn from India. That's why they say our hardware, your software will rule the world and all that. This was a slogan, by the way, not by Xi Jinping, but Wen Jiabao and the earlier leadership. In 2005 and all that, he came to India and said these things, the Chinese Prime Minister. That it will be Asian century with India and China working together and so on and so forth. And especially he said, our hardware and your software will work together and will produce great things and so on. And to the extent that they even went so far as to invite Indian companies to come there, and to many of them they gave almost free real estate. You and your office, because they had built huge cities. We build one building and call it IT, what do you call it? IT city or cyber city or something. They built huge cities, and I went to one of them in 2004-05, and they told me this is a medium-sized thing, there are 30-40 other things like that. Most of them were empty, those buildings were empty. And with all 6-lane highways and all footpaths, parks, everything ready. They are great builders, right? After all, they built a, I don't know how many 1,000-kilometer wall, so many 100,000 years ago, right? People who can build a wall, they must be really crazy. I mean, they must be great builders also. So they built the infrastructure, but they wanted to learn this part. So companies which went there and established centers, they found that the attrition rate was 25%. Right? Whereas Indian companies were used to 10%, 11% like that. Now, of course, it's changing sometimes. So the um, because they actually wanted to get people trained and take them out. Anyway, so people who didn't understand this, like for example the British press, called all Indian software business as cyber coolies. Okay? Of course, the London Underground works on Indian IT, London, their entire power system works on Indian IT, their National Health Service, NHS works on Indian IT, all that is a different story. But they put it down by calling all the leading newspapers and magazines in Britain used to call them Indian IT as cyber coolies. But it's not coolies, it's not just the wage differential which has led to these important achievements in Indian software, both in quality and quantity, but actually these skills which they developed and quite systematically and later it diffused all over the industry. So I am just going to show faces of some of them, Kohli, Ramdurai, P.P. Gupta, who was the first director, CMD of CMC, and it was this company which thought of computerizing the railways. And it is that project which touched the hearts of millions and then hundreds of millions of Indians, which changed the attitudes of India towards computers. Till that time, there was great fears about computers. Computers will take away jobs, etc., etc. Right? So it was the first project, the railway computerization, particularly reservation system, and later it became the biggest digital project in the world. Till recently, that was the biggest digital project, till Aadhaar. Now Aadhaar is the biggest digital project. So P.P. Gupta led that and he led many other things. Keshav Nori, he was a computer scientist, again from IIT Kanpur, later TIFR, and he was the first one to write the compiler for Pascal. And he was one of the articulate people who articulated all that I was explaining earlier about engineering software, okay? Software development, how to convert it to an industry. He was one of them. Narayan Murthy, Nandan, and Nandan, of course, with especially his association with Aadhaar, his leadership in Aadhaar and so on. So, of course, I am just flashing a few names and faces. There are others. Now, I'll just jump to telecom because too many important contributions have been done in telecom by Indians. Aragyaswamy Palraj, I don't know if any of you heard of him. He's actually a British Indian Navy officer. And he holds a maximum number of patents in 4G and 5G. He's now a distinguished professor in Stanford. And he developed a technology, what is called space-time multiplexing or MIMO, multiple input, multiple output. And that is the basis of these 4G, 5G technologies. That is another story. He also developed the first digital sonar in India for the Indian Navy when in 71, one of the ships was sunk by the Pakistani submarine. Okay, and then everybody in the Navy woke up and how come our sonar didn't work and all that. He was pulled out of his PhD program in IIT Delhi and sent to Naval Research Laboratory, and he developed the first digital sonar using digital signal processing, which for a long time was the most advanced sonar in the world. Sam Pitroda, you've seen him enough times on TV. I mean, I mentioned C-Dot. He was the originator of C-Dot. He had number of patents in switching, in digital switches, and that's what gave them the confidence that we can also build a switch that we need for the Indian telecom system. Vishnu Atal, a very interesting person. He studied in IIC, PhD, and then he went to Bell Labs. And there he thought of a totally revolutionary way of looking at signal, electromagnetic signal. Normally you used to do all the frequency slicing and frequency sampling and trying to compress it and so on. He said, I'm not going to look at frequency, I'll look at amplitude, which people thought was crazy. But then he developed an algorithm for that. It is called a coding system. It's called linear predictive coding. Okay, and with that coding enabled, with very low bit rates, you can have mobile telephony. So today, every single mobile phone uses the technology which was originally developed by Vishnu Atal. Manmohan Sondhi, again from IIC, went to Bell Labs. All his technology which he developed for what is called eco-cancelling. It's a multi-billion-dollar industry now, very important in the telecom networks, which are mixed, satellite, fiber, landline, etc., etc. Okay, at each interface there is eco developing. And so, Rajendra Neeraj Singh, Both are from IIT Kanpur. She is actually a chemical engineer and he was an electrical engineer. And two of them, in their spare time, that time just mobile telephony had entered United States. So around 80, 81. So on spare time, he devised one software to do network planning. How to plan the network so that, you can optimally use that spectrum which is you have got through auction or whatever, allotment or auction. So then he sent it to one of the license holders in Baltimore and DC area, and who later became a big entrepreneur and all that. So that man said, okay, how much should I pay for you? Because Americans are very, it's a very litigious society. Everybody, if you don't do something properly, the other guy will sue you sometime or the other. They're very scared of it. They said, no, how much I should pay for you? Because tomorrow you'll say you used my program without, license or without paying for it. So this fellow said, I don't know what, because I want to try this out, that's all. I don't know how to price it even. Then he said, okay, $1,500. And those days, PhD, he had just finished his PhD, and those days PhD students used to get $200, $300 monthly scholarship or assistantship. So 1,500 was a big thing. This Neera and this Rajendra Singh actually together had written it. So they said 1,500. So then that fellow said, okay, what is your company's name? I'm writing a check. These people said, we don't have a company. Right? So then they said, no, how can it be? Then how can I send it to you and, and so on. So then they concocted a company called LCC. Okay? LCC became famous because later more than 80% of all the networks in North America were built by LCC, were planned and designed by LCC, which was owned by these two, this couple. And LCC stood for Lunayach Consulting Company. Lunayach is a small village in Rajasthan from which Rajendra Singh comes. Okay, one of those Jumrutalaya types. Okay, databases. This is Nandash, worked for, 17 years in IBM in developing DB2, and then went to Oracle. He was the chief scientific officer on Oracle. Oracle, which revolutionized databases with this relational databases. Then networking, we all today use office networks, LAN, local area networks. It was Kanwal Rekhi from IIT Bombay, his company called XLAN, which developed that whole initial technology. Later it was acquired by Novell and all that. This is very interesting person. This is Bala Manian. He's brother of Narayan Vagul, who used to be chairman of ICICI. He is actually mechanical engineer, but he went to Rochester to study optics. And there, he, after I think his PhD or during his PhD, he thought of something, which is that can we, suppose we take an X-ray, can we send that X-ray, can we digitize a film and send it through telephone line to a consultant who is sitting somewhere else, and then reprint that? I mean, again, that signal is converted into film, and that man will be able to see it, because those days, this is 73, 74 period, okay? Those days it is not that some great screens were there and digital technology was there, okay? So it's not that he could see it on a screen, so he had to be again printed. So if you, can you convert film into digital signal and digital signal into film? For biomedical applications he developed it. Later, Industrial Light and Magic of George Lucas and Pixar, they acquired his patents and created a lot of special effects in Hollywood. So he was one of the first Indians to get an Oscar. In 1998, he got a technical Oscar for his contribution to cinematography, based on the work he had done, because this, George Lucas created Star Wars and all that, all the special effects started with that. Now, theoretical computer science is now today highly complex mathematics. In fact, it's so complex that now it is called complexity theory. Okay? So, Ravi Kannan from IIT Bombay is one of them. There is a whole about a dozen people who are all in the top, achieved the top honors in this field. There are 3, 4, Turing Award is one, but that is for the overall work. But there are 3 other awards: Navanlina Prize, there is a Gödel Prize, and there is a Fulkerson Prize. These are 3 major prizes for achievements in theoretical computer science, and they've all been won by this list I'm going to just flash. This is Ravi Kannan. I think now he's back in India, Microsoft researcher, something like that. This is Rajiv Motwani. By the way, he also mentored Google, and it is his paper along with Sergey Brin and Larry Page is what led to Google's technology, and later. Okay, Raju Motwani, again from IIT Kanpur. Narendra Karmarkar from IIT Bombay, he actually revolutionized linear programming with his Karmarkar algorithm. He was one of the first ones to get Fulkerson Prize, Indians. Umesh Vazirani from IIT Delhi, who is now in Berkeley. He has done outstanding work in both theoretical computer science and quantum computing. Madhusudan, he is PhD student. He is the first one to win that Nevanlena Prize, which is the highest prize you can say in theoretical computer science. He's at MIT. Sanjeev Arora, he's at Princeton. He's, I think, he's student of Vazirani again. Love Grover from IIT Delhi. Again, in quantum computing, he created one search algorithm which has revolutionized it theoretically. Manindra Agarwal in IIT Kanpur. He did his BTech, MTech, PhD in IIT Kanpur. And in 2002, he and his two students, graduate students, actually undergraduate students, wrote a paper which led to, which was called revolutionary. It hit the headlines of New York Times. And he and both his students won both the Gödel Prize and the Fulkerson Prize. Subhash Khoth, he is the second guy to get that Nevanlena Prize from Ichalkaranji in Maharashtra and studied in IIT Bombay. Anyway, so control theory, we had Vidyasagar, he was here, he established the Artificial Intelligence and Robotics Laboratory for DRDO here. Earlier he was in University of Waterloo, and he also contributed a lot in DRDO for creating the control surface for Tejas, the light combat aircraft in the LCA, which was the most important thing, in a fourth generation fighter. Satellite communications, another Indian, Pradman Kaul from Bombay, later studied in Berkeley. Later he became head of the Hughes satellite networks, and he contributed a lot to what today we call very small aperture terminals, VSAT. And everywhere you see these small things earlier to connect offices, to connect ATMs, etc. This is a satellite-based communication system. You don't need huge antennas, the small antenna will do. Okay, in storage, Praveen Chowdhury from IIT Delhi, he developed this magneto-optic memory. He got the US President's Award for that. And Sanjay Mehrotra from BITS Pilani, you might have heard of him recently. Prime Minister Modi met him because his company, Micron, is going to invest $1 billion in chip something. But his main contribution is all of us use his products. Those thumb drives, they were invented by him and 2-3 others. And established a company called SanDisk. All of us, it's called solid state storage. He revolutionized it through SanDisk and later now in Micron. Information theory, Tom Kailath is a legend in information theory from Pune Engineering College and a great professor in Stanford. Right, that's about it. These are some reference materials. These are 2 books, really, they're fantastic books. This Katie Hafner wrote on the history of internet, and Mitchell Waldrop wrote this on the history of computing and personal computing and internet and all that. Okay, thank you very much.
Thank you very much for taking us through this history of how many Indians have contributed and have developed so many things. It's a revelation to many of us, of course. And maybe since you had initially talked about what is ROS, I'll just give one story so that it encompasses many of the things that have happened. See, as he was pointing out, 1957, India was a fledgling democracy, 10 years into independence, struggling to provide food, shelter, and solve various problems. And the 2 superpowers are competing with each other, demonstrating who is mightier, who is more powerful. But at that time, we had a great visionary scientist, like what we talked about, Baba and Vikram Sarabhai, who were looking at
how this technology can be used, disruptive technology of going beyond Earth, orbiting in space, can be used for development in the country. So what Sarabhai did was, he convinced Americans that they should allow us to borrow one of their most advanced technology satellites, what was being built. And in 1975, for 1 year, India conducted the world's largest socio-technological experiment of beaming to 2,400 remote villages of our country, broadcasting, which was at that time available only to 4 metros. That was one key thing which made India realize that for a country like ours, if we were to use the existing technology of microwave towers every kilometer, not only it would have taken huge amount of money and effort, it would not have been possible to reach. So that's how the communication activity. And also you can easily see, if you talk to the people who matter, that what they speak at that time can be heard across the country. It doesn't require too much of convincing for pushing the program further. That's how INSAT series started and went ahead. Another very interesting development that happened was, Dr. Sarabhai had to convince the fishermen in Tumba Equatorial Rocket Launching Site for conducting the experiments. He was bringing in sounding rockets from, with the help of his friends, in the form of kits, get it assembled in a dilapidated church there, get it launched. For doing that activity, he had to convince the fishermen there that they should vacate the place and allow us to conduct this experiment. And for this, he had to use the services of the priests there. And then, as he had promised them that if they allow us to conduct these experiments, one day the country will benefit. Just as though what was promised, 1999 onwards, India was able to provide to its 7,500 kilometer long coastline fishermen specific information about where they can go to the ocean for fishing. And this alone saves almost 15 to 20,000 crores a year, because the fisherman doesn't have to spend extra fuel, petrol and diesel. Today, with our communication and navigation technologies, what is achieved is a small gadget which is battery operated is fitted into the boat of the fisherman, and when the fisherman is in the ocean, few kilometers away, no terrestrial tower can reach him. But a mobile in his hands communicates with this gadget, and a app in the mobile uses positional information of where he is and the prospective fishing zone information which is broadcasted through our NAVIC system, gives in the form of a video compass, directs him to go to the fishing spot. Not only that, it alerts him of the vagaries that could occur in the coming days, whether it is weather vagaries, sea state roughness being unbearable, or even if he approaches international boundaries, it tells him in his mother tongue that you have reached unsafe place or is being alerted. So you can see here India's capability of building launch vehicles, satellites and application is helping a person who does not know reading or writing do his livelihood. We have, as you are aware, millions of fishermen, and today the thing that is happening is, recently the Tamil Nadu government was forced by High Court to provide these gadgets to the fishermen, and that has happened. You can understand why these problems occur. Nobody wants to allow any new thing to come in and disrupt their whatever earnings they are doing. But then today the government is able to move ahead, and 1 lakh units are going to be built in the country and provided to the fishermen, etc. Similarly, many developments which have happened in terms of digital technology, whether it is enabling information to reach the people, railway information system, or a host of this. For doing all that, obviously we had to do a lot of technology development indigenously, though many of them may not be new ones, but then enabling the use of this technology, what is accessible to us and what is not accessible being developed here, and then providing service to the people is what has been done. And it is here that visionary people who looked at how all these technological developments can bring in better quality of life through what space is able to provide. And of course, things are changing from what was there at that time. Today, India is among the few countries which have a capability of building launch vehicles and putting it into orbit. It is aspiring to put man in space. All these are going to happen. But then India as a country, when it is looking at going from 5th largest economy to 1st largest economy, Space, which is a $1 trillion economy, you have to be a significant player, and countries moving towards that. I'll stop here because otherwise I can keep going on and on. So probably the floor is open for any of the questions you have. As you have heard, there are a huge number of Indian intellectuals who have stayed within the country and who have gone outside, who have contributed to the true spirit of Vasudhaiva Kutumbakam. Thank you.
Hello.
Yeah, please go ahead.
Thank you for a very good interaction. And my question is about quantum computing. So is there any contribution from India, any Indians, significant contribution in that area?
Is it on? Yeah. I mentioned two people, Umesh Vazirani and Love Grover, and whose contribution is already acknowledged. I'm sure many people are working both in India and United States in this field, because there are two things which drive technology in the United States and hence in the world later. One is Wall Street, other is Defense Department. War Street. Okay, almost all the chips and electronics and communication, everything as is related to missiles and war machinery, including all the telecommunication. In fact, that Vishnu Atal I mentioned, who developed that thing which we are using in all the mobile phones, he was asked by Defense Department to do military work. He said, I won't do it. He said, why? They asked him why. He said, because I go to India every year and you will send people behind me to know who I am talking to. So I won't do it. Don't want your funding. Whatever I have done is open, and you can take it further and so on. So today, why quantum computing has become of intense interest is that the cryptography which is used. How do you encrypt your signals, your communication, whether it is financial communication of the stock exchanges and all that, or whether it is military communication. That cryptography is based on the belief that no supercomputer can crack it. But the belief is a quantum computer can crack it. So that's why hundreds of millions of dollars are suddenly flowing into quantum mechanics and computer science and quantum computing. So far, of course, no quantum computer has been produced because finally theoretical work is still going on. Some elementary, what they call qubits and all that, some things are tried out. But there's a lot of funding. Whenever you say it has to do with war or finance, you'll get funding. So now quantum computing is getting a lot of funding. Umesh Vazirani and Love Grover's work is recognized. But I'm sure many more people are now working on it.
Good evening. Most of the names you mentioned are all IITs. Any non-IIT persons who has achieved anything in this field?
Oh, surely. In fact, many people who I mentioned are not from IIT. By the way, not only in technology, in business also. The first project I did, which I flashed about entrepreneurs in Silicon Valley, we ended up profiling 70 of them. And we actually finally dug into their data, personal data, and found that hardly half of them were from IIT.
Oh.
Out of 70, about 35 were from IIT, other 35 were from non-IIT, all engineering colleges. And not only that, even the IITians, none of them were toppers.
Oh, that's interesting. Yeah. Okay.
No gold medalist, silver medalist ever did anything in business or became a big entrepreneur.
Thank you.
Sir, is there information available which you just exemplified in the form of a video or book which can be used for dissemination or study, self-study also? Because this is a tremendous amount of knowledge in a very compressed format, and based on your experiences, you will have a lot of stories which are worth knowing, telling forward, generating interest, understanding where we started from to where we want. So that's intent.
Okay. See, some of it is in the book I mentioned, which I wrote, Sand to Silicon. Okay. But it is more again story of technology and how this technology has evolved globally. So all the major inventors, innovators in that are mentioned, not just Indians. But Indian work is also mentioned there, but not in any detail. So detail I am just talking, giving lectures, I have not written it down.
That is what he is trying to point out. Why don't you come out with something?
It might be a good idea for you to make a book out of it, because this is very encouraging, and this is very because it gives us hope that we have been doing work and we can continue keep on doing, and it'll transform, manifest, and then we'll be able to. So we are not alone, because it feels very lonely to be in this journey. So hence the reason why writing a book specifically in technology and Indians in technology, which have contributed significantly, will, it'll add tremendous value. Thank you.
Yeah, thanks. See, many of these stories I have written as articles. In fact, that blog address which I showed, if you go there, you'll find many of them. And in great detail, conversations with them, personal profiles of them, like Amar Bose, Rajiv Motwani, Yuvan Atik Raza, Narendra Singh Kapani. Many of their stories I have written extensively. You check my blog. Blog is not a blog. Blog, I basically put what I publish, I also put it on the blog. Okay, in the last 30 years, 95% of my articles are in my blog. Okay, but not in a book form yet. So let's see. But probably, finally I wrote that book. I don't know how many people read that book. So then I took permission from both the Tatas and the publisher and put it a free PDF copy on the on the internet. Now I don't know how many people have downloaded it and all that. So
Incidentally, there is a Kannada version. There is a Kannada version of Santa Silicon, which is done.
Yes, yes. So Government of Karnataka encouraged Kannada translation of that, and that has been done by Dr. Kamala from National College, and so it has been published in Kannada. Its name is Digital Kranti Mattu Bharata, and in fact I had the good fortune of Dr. Kiran Kumar and Radha Narasimha participate in the release of that in Bangalore in 2016. But maybe, podcasts and visual, if we do, it will have a wider audience. Let's see. I'm also too lazy in writing, easier to talk. But there is a lot of, what I said in 1 minute about one person, there's a whole story, life story. How he was shaped, what were the challenges, how he solved it, and gist of what is the technical work. Because the technical parts are too technical to be understood. But its effect, its impact can be understood.
So thanks again for sharing so many stories with us. At the end of the day, the question you ask yourself is, why would you want to know about all these, largely men, of course, apart from one woman who also did it together with a man. So why would one want to know these stories? And that's where I was wondering, when you spoke to all these men, did you get a sense of, or did they allude to, or is there any narrative, or is there any understanding of why this work, for example, cannot be done in India, right? I think, because at the end of the day, yes, the first step is, of course, fabulous. There are, we've trained people well enough that they can actually go work at the frontiers, but they're doing it elsewhere. We believe things are changing on the ground here. What is your sense of why this could not have been done in India? And has that changed at all? How do you see that landscape of what's happening in both educational institutions in India? Because you mentioned IITs, you mentioned IISc, you mentioned BITS Pilani. Bangalore is called India's Silicon Valley. So how does all of this compute, at the end of the day?
Okay. For the first part, why should we know this? That he also raised that question. That is, it is inspiring, and that is the reason, in fact, Tata supported it. And once they said that this will be inspiring for the youth, they just went ahead and supported it and never interfered on what I wrote. Because I was not writing about Tatas. Okay, many companies will fund it if you are writing about them. But just because they thought it will have an inspirational value. And of course, in the beginning, I also didn't know, but I believed that a lot of work has been done. But definitely, even Mr. Tata told me after it was released, he said, I knew 2 or 3 names, I didn't know so many Indians have done so much work, etc. And of such quality and depth, etc. So, the fact that Indians and people educated in India, see, none of these are second generation, third generation Indians, even when you talk about those. There are many, I'm sure, who are coming up now. But that our own education, from our own education system, or despite our education system, we have produced people who are, as good or better than anybody else in the world. So that feeling, because we have been weighed down by this whole Eurocentric view about everything in science and technology, that all ideas, everything has come from rationality, science has come from Europe. And we can only try to catch up and do secondary work, take to the next decimal place and that type of thing, okay? That innovative work cannot be done. All that, this thing was there and is still there to quite an extent. But other thing, the question you asked, most of these people went in the 60s and 70s. In the 60s and 70s, both technologically, competitive teaching and research was in the United States. And the market which demanded products, demanded solutions was also in the United States. Both the Wall Street and the Wall Street were in the United States, which are funding it. Okay? So that is the reason, not just Indians. I mean, in fact, you talk to the Brits, they say we do the science and the Americans do the technology. Because there is a huge migration of talented people from Britain to United States. Not just in the World War, now also, So, for a long time, United States was the only place which had that academic atmosphere to do cutting-edge technological work, and also the market which demanded solutions and products. So, both tech entrepreneurs also could flourish there. India didn't have that situation. Whereas now, we have a large technology-consuming population. Okay? If you have a billion or a billion and a quarter mobile phones, and all almost linked to the internet, and so on, then based on that, you can provide services, and that is the kind of startups and innovative work that are largely coming up. Of course, there are a few which are coming up in space. He was telling me some who are even working on rocketry, which is a very, I would say dangerous field. Because if you see the history of rocketry, a lot of it has ended up in explosions when they were trying to do it. And civilians engaging in such explosive things is a very, the fact that government has allowed these things itself is a big step, big risk they are taking. Otherwise, so far, even in the United States, the private sector is to participate, but all the rocketry and missiles and all that, main work used to be done by NASA or in the Defense Department. Boeing and others used to contribute to that. So now we are consumers, but we are still not producers of technology. And we're still not, if you say, I'm putting 0.6% of our GDP into S&T research, then what would you expect? If China is where it is or South Korea is where it is because they invested in education, they invested in research. We are not investing in that. So whatever we produce also, half of them, so it is a fact that because of globalization, some of them want to come back or link up and network and then, also help the startups here or come back and settle back here is a effect of globalization and also improved quality of life here for certain sections and so on. But, I mean, our IITs and BITS and many other engineering colleges are next to nobody. In fact, this Motwani, who was PhD from Berkeley, did his BTech in IIT Kanpur, and he was a director of graduate studies in Stanford in computer science, right? He told me, he went on record to say the undergraduate education he got in Kanpur was much better than whatever he saw in both Berkeley and Stanford. Whereas for all our kids, Berkeley and Stanford are, are ideal, and MIT and so on, right? But that is only undergraduate education. What about postgraduate and research? We are still a long way to catch up, and they're still underfunded. I mean, you talk to anybody in IIC or IIT, people who are actually struggling to get funds. Sometimes they don't get funds. Sometimes funds get sanctioned, it doesn't reach them. There are huge number of senior research SRFs and JRFs who have struggled through NET and all that, and finally, got that scholarship to do PhD. And there are so many Twitter messages which come, 6 months I have not received my scholarship. And these are supposed to be the best cream of the research scholars. So if, we cannot expect something magical to happen just like that. So still whatever is being done, and even in being in the government structure, organizations, within organizations like ISRO and Atomic Energy and all that, so much work under very hard conditions they could do, and they are motivated to do. I'm sure, just like many of the people I mentioned, all these people could have also migrated. They would have been in Silicon Valley or somewhere else in some academia if they wanted. But they stuck around, and maybe they have, you can say, they get great satisfaction that they have contributed to the nation, and they also had done something which is concrete. Okay, not one screw in a big machine, not a cog in the, a lot of research work is like that, cog in the, big machine. Whereas here you can actually, bottoms up, you can do turnkey, certain products, certain services, certain systems and all that. So, like for example, you can build a stock exchange in India, right? They will not allow you to touch NYSE. They will give you a small piece of that to do it, or NASDAQ can do it, and you say we are doing software work for NYSE and all. They will not allow you to build a NYSE in any country, right? But you could do it in India. You could build a Aadhaar system. You could build a passport seva system. So this kind of applications, which are absolutely global quality, not just global in size and scale, have been done in India by people working here. And that is remarkable. The whole, actually in the 90s, I remember, there used to be large number of delegations from so many countries, both European and China and Russia, to come and look at our NSE, how the NSE works. How did you dematerialize shares so fast when even the US didn't do it so fast? So in the financial systems, we were able to modernize it very fast, and it's top class. Okay, but in other actual hard technologies like semiconductors, chips, and so many other things which we are not invested. I mean, today, for example, there was a news item, right? We found lithium in Jammu or something like that. And we are waiting for some Chilean company to come and tell us how to develop that. Because we are not invested in how to do rare earth work. We have a rare earth India Limited for, 4 decades or 5 decades, in Kerala, working in Kerala and elsewhere. But we didn't invest in rare earths required for the semiconductor industry and all that, which China did. So today China is in the pole position. China can cut off, yesterday they cut off germanium and gallium exports, which will affect the electronics industry and many other industries elsewhere. So we need to invest more. Government has to invest more, because that investment has to go into academic institutions as well as labs. Then, and for research funding has to happen. Then people will stay back to do. I mean, why not? If you look at purchasing power parity, what is it? Can you be a university professor, can have a decent life in India, right?
Thank you, Mr. Shivanand and Mr. Kiran, for such an insightful conversation. And thank you all for coming.